Exercise. Find the max domain of R of t. Is this vector function continuous? If it is, use the code above to plot the curve parametrized by R. We can find the domain of R by finding the domain of each component function and taking the intersections of their domains. The first component is the square root of 16 minus t, so that t has to be smaller or equal to 16. The second component is the square root of t minus 2, so that t has to be greater or equal to 2. So the domain of R is the closed interval from 2 to 16. Both component functions are continuous in this domain, so is the vector function. We need to input this specific domain to plot the following curve. Exercise. Use the code above to animate a point moving accordingly to these functions. The three vector functions parameterize the same line segment. To produce the animations, it is necessary to change the domain A, B in the code and the axis limits to show the starting point -1, 0 and the end point 3, 4. We do this by making x.axis equal to -1.4, 3.4, -0.4, 4.4. It might be good to also change the number of points n. I took 1000. The animations show the vector functions parametrizing the same line segment, from -1, 0 to 3, 4, but with different speeds. Exercise. Change the code above to plot the space curves given by the functions below. For this exercise we need to change the domain, and do this by changing the parameter t equals np.linspace from 0 to 6.283, or 1.845, and the dataset x, y and z to the respective sine and cosine. Both cases show an inclined circle. Exercise. Find three different parametrizations for the curve R, with t and 0 to pi. For this exercise we could change t in any way we please, as long we make the respective change in the domain. For example, we could make R of t equals sine of 2t, cosine of 2t, 2t squared divided by 4, with t in 0 pi. Another possibility would be to replace t by square root of t, to get R of t equals sine of square root of t, cosine of square root of t, square root of t squared, which is t in this domain, divided by 4, with t in 0 to pi squared. Yet, we could make R of t equals sine of 4t, cosine of 4t, 4t squared divided by 4, with t in 0 pi over 2. For the three cases, we verify that the curve plotted is the same.